Hello student, welcome to the web optics course. So today we will going to discuss this Jones matrix formalism that we have been discussing for last few classes. So we will continue with this. So we have lecture number 59 and we will continue our discussion on Jones matrix, which is important. So Jones matrix we formulate for linear polarization. One thing we did not do, so that I am going to do today. So let me remind what we had for linear polarizer. Linear polarizer means if I, so this is the system, optical system that can polarize the light. So this is the polarizer. So this polarizer can have a certain path axis. Say this is the path axis, and if I launch a light, a unpolarized light, light get polarized here. And this polarizer can be defined by a matrix, and that matrix is our Jones matrix. Also the light that will produce the linear polarized light, it can be represented also this matrix form, which is forming a vector, and whatever the light we get at the output, if this is the E, that is the light we are getting at the output, this is a specific notation we call this is a Dirac notation, but this is the output light, that will be the polarizer operator, that is the matrix that is defined, that is defining this the nature of the polarizer, and the input light. So that is the recipe we have been using, and different cases we determine what is the matrix for M. But one thing we did not do yet, and that was we supposed to do in earlier classes, but somehow we missed that. And so let me give the example of this M matrix for different cases. For example, here M was 1 0 0 0, if you remember. So that basically when the linear polarizer has TA, that is transfer axis or path axis along x direction or along x direction. Similarly, M was 0 0 0 1 when the linear polarizer having their TA or path axis along y direction. Okay. And when this path axis is 45 degree making a 45 degree angle, then it was simply 1 1 1 1. That was the structure with certain factor half, and that is when linear polarizer has its transfer axis or pass axis making 45-degree angle with say x axis. So, this we discuss, but today we will going to do something interesting, something which I did not do earlier, and that is Jones matrix for circular polarizer. So, what is the meaning of Jones matrix for circular polarizer? The thing is here so we have a polarizer here, and this polarizer what it does is, if I launch a polarized light with any arbitrary polarization, then in this side we will always get a circularly polarized light. So, now the question is, what is M here? How to calculate the M for this case? So, let us start with right circularly polarized light. So, for right circularly, so right circular polarizer, right circular polarizer, that is the polarizer that makes any arbitrary polarization to right circular polarization after, if this is through this system, if the linear or any kind of polarized light is passing through, then the output we always get the right circular polarization. So, for that, so what we have in order to find out, so our aim is to find out M. So, what should be the first condition? That if I launch a right circularly polarized light, then allow it to pass through this system, then in the output I always get a right circularly polarized light. That is the condition, first condition. And second condition is that since it is producing right circularly polarized light, if I launch a left circularly polarized light which is perpendicular to the right circularly polarized light, these two are orthogonal to each other, then here we are going to get 0. So, nothing will come, exactly like linear polarization. If I have a linear polarization, the way we calculate the linear polarization with vertical pass axis and horizontal pass axis, what should be the form we calculated, exactly the similar way we are going to calculate by considering these two conditions. Now, we consider, after having this, we consider my M matrix is A, B, C, D simply. So, we need to find out A, B, C, D. This value we need to find out using these two conditions 1 and 2. So, let us do that quickly. So, from condition 1, what I get is A, B, C, D, and this matrix that I am writing here 1 minus I is representing the right circularly polarized light. So, it will produce a right circularly polarized light because I am trying to find out the value of M for right circular polarizer. So, that is from 1, that is the equation one can have, and then I can get to algebraic equation like this: A minus IB is equal to 1 and C minus ID is equal to minus I. So, a set of equation I write it 3. Also, from condition 2 I can get a similar kind of thing, but here instead of having right circular polarized light, I put a left circular polarized light which is orthogonal to the right circular polarized light. So, that means I can have here 0 0 because it is not going to. So, that light will not be allowed by this polarizer. So, I will get another set of equation which is A is equal to minus IB and C is equal to minus ID. So, here we have 4 unknown A, B, C, D and we have 4 equation, a set of equation in 3 and a set of equation in as 4, and we can use this. So, once we have A equal to this, and if I replace this thing to equation 3, so from equation set of equation 3 and 4, we can readily get, if I replace this, so I can get minus of 2 I B is equal to 1, and that gives me simply B equal to 1 by minus of 2 I, or if I multiply I both side, so 1 by 2 multiplied by I with a plus sign, that. Similarly, if I put C, then we get minus of 2 I D, that is equal to how much? Minus of I. So, from here I can get D equal to I, minus minus will cancel out, I will cancel out, D equal to half. So, I get B equal to I by 2, D equal to half, and that value again if I put in equation 4, then that gives me simply A equal to, we have A equal to minus of I B that we get, and B is equal to I by 2. So, it is minus of I multiplied by I by 2. So, this is half. So, my A is half, and C which is minus of I D. So, I have minus of I, and D, what D value we got, D is half. So, it is simply half. So, A, B, C, D we calculate. So, my M matrix, if I take half common, should be half of A is 1, B is what was B? My B was I, if I take half common. So, here we have I, C is minus I, and D was half. So, 1. So, this is the matrix we have, and this matrix corresponds to right circular polarizer. In a similar way, for left circular polarizer, the Jones matrix M will be, I am not doing that, I strongly suggest exactly in the same way I calculated here, exactly the same way one can calculate this, the student should calculate it. The condition exactly the way we put, it should be put that M that will operate over left circularly polarized light will produce a left circularly polarized light, that is condition 1, and condition 2 that M, if it is operate over a right circularly polarized light, will get 0, because it is orthogonal to left circularly polarized light. So, these thing I wanted to show in today's class, because that was missing, and we can also check that actually that for any arbitrary polarization whether this is happening or not. So, let us do that. So, for example, our M for right circular polarized light is this. So, M for right circularly polarized light, we know this is half 1 I minus I 1, that is the matrix that is defining the right circular polarizer, and any arbitrary polarized light, this is the most general polarized light I am writing now, which is elliptically polarized light. So, I A B plus I C. So, that is a elliptically polarized light. So, what I am doing that, okay, let me draw this scenario. This is my right circular polarized optical element that polarizes the light in right circular direction, and what I am doing here is I am launching a light which is elliptically polarized. So, the polarization here is elliptical, a general form. So, I am just drawing a elliptical shape here, and now this polarized light is allowed to pass through this system, and what I get in the output is a circularly polarized light. Not only circularly, it should be a right circularly polarized light. This is z direction. So, that I am going to get. So, let us do whether I am really going to get or not. So, what I do is I put this m value. So, half of 1 I minus I, and this I put, which is A, and then B plus IC. So, that means I am operating M over this E. So, that thing is this one. So, what I have here, so here I am getting like half of A, then minus C plus IB that I get, and another I get minus of IA plus B plus IC. That is the value I get in the right hand side. But this I can do in this way, I can write it. If I take common A minus C plus IB, if I take it common outside, then inside the matrix what I get is interesting, and that is 1 and minus I. Note that if I multiply A minus C plus IB with minus I, then I am going to get this value which is here, and this is if I want to find out the state of polarization, this is nothing but a right circular polarized light. So, that tells us that our right circular polarizer can be defined by a matrix with this particular form. Obviously, half will be there, half 1 I minus I 1. So, this is the way the right circularly polarized light can be generated by using a system which can polarize the light in the right circular direction. Well, now I quickly summarize the Jones vectors that is generated, and summary of the Jones vector for all the cases quickly, like we did for the polarizer and phase retarder and phase and rotator. For these optical systems we do. Now, here we will list out the Jones matrix for Jones vector rather for all the all kind of polarization. So, summary of Jones vectors. These are not matrix, but vectors for different polarization, for different state of polarization. Different state of polarization. Now, check it. So, linear polarization, the general form, if it is x direction, y direction, and this is the way it is vibrating. The general form is cos alpha sin alpha, where this is alpha, and special case when it is vibrating along x direction, E naught will be 0 1 sorry 1 0. When it is vibrating along y direction, it should be 0 1, and when it is vibrating with 45-degree angle, this angle is 45 degree, then I can write it as with a normalization factor 1 1. That is for linear polarized light. Now, what happened if I put a circularly polarized light? Circular polarization. For circular polarization, we have two state. One is left circularly polarized light and can be defined by this, and another is right circularly polarized light defined by this. These are two. Then also we can have elliptically polarized light. Let me do that in a different page. Then we have elliptically polarized light. In elliptically polarized light, we have ellipse whose major and minor axis is coinciding with the x and y axis. So, this is x, this is y. So, E0x is A and E0y is B, and A here is less than B. One case also we can have with this orientation, where x and y, where A is greater than B. But the general form is E naught tilde 1 by for normalization factor I put this, and A I B, and that is for either left circularly, either this system depending on the value of A and B, or this system, but both the cases it is left circularly polarized light. So, symbol will be this. So, this is left, not circularly, left elliptically polarized light. Similarly, if I have this notation, this structure, depending on the value of A and B, I can have two structure, either this or this, but here it will be it will be right elliptically polarized light. That is when the major axis and the minor axis coinciding with x and y axis. A more general condition can be figured out, and that is when, suppose this is my x axis, this is y axis, and the ellipse is defined in this way, and it is suppose moving in this direction. So, E will be 1 divided by root over s square plus c square, and it should be a b plus I c, and that is again it is moving in this. So, again it is a left circularly polarized light, left elliptically polarized light, but the thing is here x and y axis are not coinciding x and y axis. The major and minor axis of the ellipse does not coincide with x and y axis. In a similar way, we can have another orientation with opposite direction. This is right elliptically polarization x and y, and E will be very much same. Only thing is that we have a minus sign here, minus I c, and the angle also, this angle, whatever the angle it is making, we can figure out here. For example, E 0 x or x 0 whatever is A, and E 0 y is this, and the delta will be tan inverse of C by B. This delta is a phase of these two components, and yeah, so this is, we can generalize all these things, and we can also figure out the angle actually. So, that angle is tan. So, if this angle is alpha, then tan of 2 alpha as per our expression, this is 2 of, let me write down first, E 0 x E 0 y whole divided by E 0 x square minus E 0 y square, and then we have cos of delta. So, cos of delta you can find out with C and B. E 0 x is A, E 0 y is B square plus C square root over of that, and this is the quantity. So, using that one can find out what is the value of the alpha, and with exploiting this expression which is written. So, if a general matrix is given in this way, A plus A and B plus I c or B minus I c. So, one can understand readily that this is an equation of this is representing a polarized light, and this polarized light is elliptically polarized. Whether it is a left elliptically polarized or right elliptically polarized, you can find out from this sign. And what are the values of these angles alpha, and what is the phase lag between these two components, and what are the amplitude of these, one can figure out everything from this matrix notation only. So, with that note, I would like to conclude today's class because I do not have much time. So, in the next class we will try to understand that how polarization can be done. So, what is the way to polarize the light, that thing we will not going to understand. So, beforehand we study the matrix method, Jones matrix method, which is very important to systematically understand the polarization of the light. Now, we are in a position to understand that how light polarization can be mathematically represented. So, now we will going to discuss how in fact polarization can be done, what is the way through which we can polarize light. So, with that note I would like to conclude here. Thank you very much for your attention and see you in the next class.